Everyone. So today is day 17 of the challenge, doing 30 deep learning projects in 30 days. So the problem is about where we have to build an LSTM model for sentiment analysis on IMDb Dataset. So let's go and do what? Use the chat GPT here and say, hey, today is day 17 and here is the problem statement. So I'm using the same context window so that ChatGPT would know, okay, this is different. Um, Let me go read a little about it. It says we have to do what? We have to import the libraries. These libraries we'll be importing. Uh, then what are we going to download the database from? We can not database data set from. So we'll be downloading. We'll get the data set from this IMDb tensorflow.keras.dataset IMDb. So we'll load the data. Okay. Um, okay. So then we are going to have uh, pre-process the data. I'll go and see what is this pad sequences. I've never used it before. Then we will build the LSTM model. This is looking pretty normal, but this is something I'll be doing for the first time. And then once done, compile the model, train the model, evaluate the model, and then look at the loss. Before that, it makes sense, but before, can you just give me not in .md? Can you just explain in easy words to me what LSTM is and how it works? So yesterday we saw that when we were doing our first problem on the RNN, we saw that LSTM is an advanced model and also works on the time series dataset or sequential dataset basically. So how is it different from the RNN recurrent neural network? We are going to figure it out today. So it says LSTM is a long short term memory in the simplest way possible is the model. So LSTM is a type of recurrent neural network that's specially designed to handle sequential data. Okay. Regular RNN struggle with remembering long term dependencies. That's what we have learned yesterday. They tend to forget what happened earlier in a long sequence. LSTM solved this problem by having a better memory system, allowing them to remember information for long periods. Okay. So LSTM, what difference it has from the RNN that we have worked and explored yesterday is that it has better memory system, and that allows it to store the memory for the longer periods. Think of an LSTM as a smart memory box that can decide what information to keep and what to forget, and what to pass on to the next step. This makes LSTMs very good at tasks like understanding text, making predictions from time series data, or analyzing speech. Okay, so it is a good choice because it has a smart box that can remember information for a longer period of time. Um, so because of that, it is really good at predictions from the time series data and analyzing speech, anything where the context of the sequence are involved. How does it work? So LSTMs are like complex versions of the standard RNN that we have learned yesterday, with a more advanced mechanism to decide what to do with information. Cell state, okay, it has these things. First is cell state. This is like the memory of the LSTM. It carries useful information throughout the entire sequence, which allows LSTM to remember things for a long time. Okay, so the first phase is cell state. So this is like the memory of the LSTM. So it carries useful information throughout the entire sequence, which allows, so it carries the useful information throughout the LSTM sequence, entire sequence, which allows LSTM to remember things for a longer period of time. Okay, so this carries the information. This is the memory bus, we can say. Then we have gates. LSTM uses gates to manage their memory. Gates are just small neural network that decide what information should be kept or discarded. There are three types of gates: forget gate, input gate, output gate. Okay. The input forget gate is that it decides what information should be forgotten from a null from a cell state. Okay. From the cell state, what information should be forgotten is decided from this state, this gate. Think of this as a deciding as deciding to erase something from the memory that's no longer useful. Okay. Then input gate, it decides what new information should be added to the memory. And output gate, it decides what information to output at this step. This means that that every that at every point the LSTM decides what it should produce as the final result. Okay, so it has two information. If LSTM, the model recurrent neural network model, has the information, so it is going to carry this information throughout the entire sequence, uh, in this state called cell state. Next, we have three gates: forget gate, input gate, and output gate. Forget gate is to decide what information to delete from the cell state. Input gate is used to decide what information should be added to the cell state. What information should be deleted to the cell state? Forget gate. What information should be added to the cell state is input gate, and what information to output at this step is called output gate. Okay. So now we have to imagine how it works. Imagine we are reading a long story. Okay. We are trying to summarize what happened in each paragraph to understand the overall plot. Okay. As you read each paragraph, you decide whether the details are important or should be remembered or not. As I read each paragraph, as I read each paragraph, I decide whether the details are important, okay, or should I forget them. You keep a summary notebook where you add new details that are important, and that is we output the details that are important, and you decide whether the old details are in the new notebook are still useful or should be forgotten. Every time someone asks you to summarize where you are in the story, you output a summary based on what's currently in your memory. Okay, see, here in this, suppose we have watched a movie called, let's say, a recent movie. My parents recently watched a movie called Bhool Bhulaiya 3. So now I'm asking them to narrate the story to me. So how they are going to narrate the story to me? They will first do what they, while they are watching, they'll decide what is the information, important information that they have to share, and what are the details that they should not tell, that do not add much to the story. So they'll delete them, they'll forget them. Now at each step, they'll think of, okay, this is the information that I need to output. This is the summary of the story that I need to output at every step, is what the output gate is intended to do. So this is exactly what an LSTM does. It reads a sequence, remembers important information, forgets unnecessary parts, and provide an output based on what it knows so far. So it keeps track of the information. It has three gates, um, and with the help of those gates, it decides what information to add, what information to delete, which is no longer needed or is unnecessary, and what information to output based on these two things. The two important features of the LSTM is the gates and cell state, which is the memory that keeps a running summary of what's important from the past. Gates act like filters that decide what should be remembered, added, or forgotten. Okay, so it looks like really easy, but it is not, because I don't have a visual representation. Okay, anything without visual representation is something I think that is something we need more clarity. Maybe after doing this challenge, I'll dig little deeper into understanding theory of each model, because by the end of this challenge, I would have solved 30 plus 60 machine learning problems, covering ML and DL, which is machine learning and deep learning. So I'm really excited to see what I'm going to do after finishing this challenge. So yeah, maybe then I can dig a little deeper into going and understanding the theory. But for now, I understand that how it works. It makes the use of memory, cell state, and gates to decide how to present the memory, how to make use of the important information from the cell state, and use gates to output the important information. Uh, and then we if we read a little about why is this useful, because we read that LSTMs can handle long dependencies much better than regular RNNs. For example, in a movie review, the sentiments, positives or negatives, might be influenced by a word that appeared far back in the review. LSTMs can remember this word even after many other words have been processed. Okay, it says that, let's say a movie has a lot of words that are presented in the form of dialogues. So LSTM, with the help of LSTM, a word that has been spoken or used in the like starting beginning of the movie can be remembered at the end, by the end of the movie. So that is why LSTMs are useful. So what I do understand what this is. So let's start with solving the problem. If I read the, let me, what, yeah, let me read it. It says, we will build an LSTM long short term memory model for sentiment analysis using the IMDb movie reviews dataset. If you remember, when we were doing this machine learning challenge, we have solved this problem. But yeah, uh, let me see if we have solved in the same way. But yeah, I'm going to continue with this. Sentiment analysis aim to determine whether the sentiment of a movie review is positive or negative. Okay, so there are two options, positive, negative. So that means it is a classification type problem. We have to estimate the sentiments into negative and positive classes. Now, what is LSTM? We have already gone through it, but we can read it one more time. It says that it is special type of recurrent neural network that are especially good at learning from the long term dependencies. Unlike standard RNNs, LSTMs can remember information for longer periods, which makes them ideal for tasks involving text sequence like sentiment analysis. Okay, so let's start with coding. Let's start with coding, and we will understand every new term that will come our way. So the name of the file is day17.py. Let's add it to our script, mention what the problem is. So it is going to be problem is, let's copy the problem from here. Give me a second, I want to drink water. Okay, now let's import the library. So import tensorflow as df, import numpy as np, from TensorFlow, Keras dataset, import IMDb. From preprocessing sequence, import pad sequences. I don't know why we're using it. We are using it to make sure all input sequences are of the same length. Okay. Then model, sequential model, then layers, embedding layer, LSTM, dense and dropout layer. Okay. From TensorFlow keras pre-processing. Which one? Sequence import pad sequence from TensorFlow keras models import sequential model from TensorFlow keras layers import embedding dense dropout and what else LSTM. And to visualize import matplot pyplot as plt. The step one is done. Now we need to load and preprocess the IMDb dataset. Load and preprocess the dataset. So it comes with pre-tokenized data, so we need to load it and prepare it for training. So we vocabulary size, we need to restrict the vocabulary to the 10,000 most common words. Uh, cap caps not vocab size, and then x train x validation data y validation. Okay, imdb dot load. Here we mention the vocabulary number of words are going to be vocab size. So how many unique common words it is going to have? 10,000, can have even more than that, so we need to restrict that. Now we will apply pad sequences. Uh, so it is going to load only the 10,000 most common words. Load IMDb data with common thousand only, with only 10,000 common words. Okay. So let's do what before I apply pad sequences, because since the reviews has different length, so we have to make them all words 2,200 words long. Shorter reviews with zeros while longer reviews are truncated. So what we are doing, we are applying padding. So if let's say I have, say pad sequences of 10 and I have a text as hey Akansha, how many words character it has, words it has. I let's say I say 5 words, 5 words, so it has 10, 1 2 words. Okay, then it is going to empty with shorter will be added padded with 0, so it will be 0 0 0. So this will be the padded version. Now let's say it is going to have here Kansha, how are you doing today? Uh, I hope all is good with you. So here how many words we have? 1, 2, 3, 4, 5, 6, 7. Let's remove this. And 8, 9, 10, 11, 12, 13, 14. I have 14 words. This is beyond the limit restriction. So what I'm going to do, I'm going to, after applying padding, it is going to truncate the extra words. So it is going to stop at this. Hey Akansha, how are you? 5 words. So this is what truncate pad sequences will do. So let's do what? Let's mention the length 200. So I'll say padding sequence sequences to ensure and ensure uniform length of reviews. Okay, so here the X train will become pad sequence. Um, Mention the X train. Uh, Max length is max length, and the padding, where do we have to add padding? Post the at the post the words, and then we do the same with X validation. Pad sequences X validation, max length, padding, post. Okay, then what are we going to do? We are going to define the LSTM model. Define the LSTM model. So we'll do model is equals to LSTM. Okay, and then we'll add the first layer on this model dot add embedding layer, not to this embedding layer. Here we mention what is this embedding layer. This embedding layer is added to convert the word indices into dense vectors. Okay, it converts word indices to dense vectors of fixed length, which is 128 dimension. This layer learns an embedding representation of for each word during training. Let me go and Google a little about it. Let's see what this embedding layer is. Turns non-negative integers, that is indexes, into dense vectors of fixed size. So 4 will become 0. So the non-negative integers will become something like a dimensional vector that we mention here, like this: 0.251 6. Nice. And how it is converted? So they are converted from this to this, but how? As in what formula it has used? I am going to ask, because this is the only new thing that we'll be doing today. So let me come out of it. I'll say I want to. Let me. Can you give me a second? Let me go and close the window. I want to understand how this is done. How the new vector size is decided. Vector size or values are decided. Can you explain with easy language without maths? Not easy maths will work, complex maths. Okay, so the embedding layer is used to convert the words, which are originally represented as numbers or indices, into dense vectors that we just saw, that capture the meaning of the words. These vectors are basically representation. Oh, this is embedding layer. Oh, my bad. I've been using this layer like a number of times when we were studying the RAG implementation. But even then, so what this embedding layer does, it converts the words into vectors so that the model can understand. So these vectors are basically representation of the words that are neural network that the neural network can understand relationships between. Imagine we have a dictionary of words and each word is assigned a unique number. For example, let's say happy is assigned a unique number of 7, sad is assigned 3, dog is assigned 50. This number representation does not tell you much about the word itself. Yes. For example, the number 7 for happy does not say how similar or different it is from the other word. Okay, correct. That's where an embedding helps. It translates the number into meaningful vectors that are more useful for neural network. Correct. So it converts words into numerical representation or of vectors of dimensions that we will specify. And why this is useful? For example, happy is represented by a number 7, sad is represented by a number 3, dog is represented by a number 15. Now, the model will not differentiate between happy, sad, and dog because it does not know the meaning. For the model 7, 3, and 15 are three different unique numbers. And that is the main intent. The model should keep them, should not favor any number, should not favor any word. So, that is how embedding helps. How does it work? So, this is the total number of unique words in your vocabulary. How many unique words we have? We have already specified vocabulary by vocabulary size. How where also we have used it? We used it when we were loading the data. There also we had specified 10,000 vocabulary size we are going to go ahead with. Then if the vocabulary size is 10,000, it means that there are going to be 10,000 unique words in my data set that we mentioned. The output dimension is going to be 128. This is the size of the vectors that represent each word. Okay. It means each word will be represented as a vector of 28 numbers. Think of this as turning each word into a point in the 1 to 8 dimensional space. Correct. Now the max input is going to be the maximum length. So the maximum length in each input is going to be that we had used here also when we applied pad sequence 200. So the length of the each input sequence is going to be 200. How does this work? Suppose you have a vocabulary of 10,000 words and you want each word to be represented by a 28 dimensional vector. When you pass the word happy to the embedding layer, it will look up the 28 values that represent happy. Okay. This vector is learned during training, meaning the network will adjust the 128 numbers in such a way that the words with similar meaning end up having similar. Okay, so this is all will come from the formula, I guess. So what it does, it puts the similar words around similar things into 128 numbers. So for example, happy, smile, laugh will all be placed together. uh, uh, yeah, because they all have similar meanings. Now imagine we want to represent words in three dimensional vectors for simplicity. Initially, the number for happy might look like 0. 0.1, 0. 0.5, and 0. 0.3. Another joyful might be so the each word will be represented into three dimension vector. Joyful might be represented like this. During training the network will adjust these numbers so that happy, joyful end up with similar vectors. So they are because they have similar meanings. Correct. Let's do what? Embedding. I'll show you. Embedding in machine learning. This is how, so the words might look like. See, this is how they are placed in the 3 dimensions. Scattered, but similar words will be scattered, will be placed together. So yeah, I do understand what embedding is. So we can go back to this. This is different. Let's understand this. Yes, let's add the embedding layer to convert the words into embedding. So here we mentioned the embedding dimension is going to be embedding dimension is going to be 128 dimension vector. So I'll say here it is going to be embedding dimension is going to be, sorry, input input dimension is vocabulary size that we have decided, which is 10,000 words. Then we have output dimension. We want it into one size of 128 vectors. And then we have input shape is going to be, sorry, before input shape, input, not 128, embedding dimension, input length is going to be max length. Okay, correct. So then we are going to add, we have added an embedding layer which will convert the words into a vector size of 1828. Then we have model dot add uh, dense layer, I guess. No, LSTM layer. That LSTM layer of 128 neurons where the return sequence is going to be false. And what it says, the LSTM layer has 128 neurons, which means it can learn complex relationship in the input sequence. Then we will add the dropout layer, dropout layer to randomly drop 50% of neurons to prevent overfitting. Then we will have the output layer for our prediction, which is going to be a two, I guess, one layer. The function is going to be sigmoid function. Why? Because we want to tell whether the number is a positive, whether the is 0 or 1, whether the review is 0, positive or negative. So for binary classification, this activation function is generally used. Then we will see the model dot summary. Just give me a second, I have my cat doing something fishy. I'm so sorry. Okay, so we have added the code for to see the module summary. Now we are going to compile the code. So compile the model. Let's do what? Let's put this thing in the center. The what we are compiling, what we are writing. Model dot compile. Here we mention the optimizer, Adam. Then we mention the loss. The loss is um, binary cross entropy. It is a classification type problem where we need to decide whether the number is whether the review is positive or negative. So that is why the loss is this binary cross entropy. Then again we have a classification type problem, so we'll go with metrics, and we want to our model to have monitor accuracy. So we'll do what now? We train the so we simply train the model and store the training in the history. function, history word. Here we mention the training data, X train, Y train, the validation, not validation, epochs, epochs are going to be 5. Then batch size, the CH size is going to be 64. Then do we want validation expression data is going to be X validation, Y validation, and verbose is going to be 1, which means that yes, we want to see the output for each epoch when the model is training. And then we evaluate the model by getting the, or what we can do, we can evaluate the model by doing what, like we can skip this step because we are passing the validation data here only. So I'm not, I don't want to evaluate the model here on the validation unseen data how the model is performing. I'm passing it here only to see the validation information, the data of the validation, the information on the validation data. And then we simply visualize it, and there we can identify how the model is performing, how we can evaluate. They are looking at the loss, the plot the loss, visualization by plotting the loss. So we'll say figure, the size is going to be 10 is to 6. Here the plot is going to be history loss, label is going to be training loss, plot history history loss for the validation data loss, and the label is going to be validation loss. Then we do what, the X label is going to be epochs, the Y label is going to be, what are we looking at, loss. The title for the graph is going to be the training and validation loss of LSTM model. And then we also see which line represents what by using this function, and then we show it. And that is it. Let's go and run this. Python base 17. Let's see if we get any error, because we have done what, we have experimented a little with the code, but we have not blindly followed the code of GPT. That's why we have an error. So it says what it does, it says we have an error. So here it is a sequential model, and we are adding an LSTM layer. Let's do what, run it again. So we see the model summary. We have the first layer, embedding layer, which is converting the vectors, sorry, words into vectors that the neural network can understand. Then we have LSTM layer to to have create a sequence of memory by applying the filters of gates. And then we have a dropout layer to prevent the overfitting. And then we have the dense output layer to give us the output whether the review was positive or negative by using sigmoid activation function. Each epoch is going to take some time, around 40 seconds. So I would recommend to go and do what, not even 41 minute is it is taking. So I'll recommend to go and fast forward it to at least 4 minutes. And yes, yes, please fast forward it to 4 minutes. You Yes, because I'm not going to edit it. I do want to keep it for myself to come back to this video and revise if needed. I don't think it's going to be needed, but yeah. So it has stopped. Very, very bad thing. Okay, thank God. See, so the initial loss was 0.6, accuracy 65%, validation loss 0.48. Validation accuracy is really good, which is a good sign. It is 79%. So we are on the second epoch. It is also going to take somewhat around 1 minute 10 seconds. So what I can do, I can pause this video and then I can resume once the epoch, all the five epochs are done. Okay, so it has completed all the epochs. So what we can do, we can look at the information from the terminal. So the loss was started with the on the training loss started with 0.60 and ended with 0.57, not that much decrease. But the accuracy also increased from 65% to 67%. The validation loss though has increased, which is not a good sign, and also the validation accuracy also dropped, which is also not a good sign. So our model did not perform as we have expected. So see the validation on the validation unseen data, it is not performing that greatly. So yes, but what we can do, maybe we can explore a little with changing these parameters. Not here. Here maybe increase the epochs or decrease the batch size. So maybe that way, if we hype or we can also apply hyper tuning to find out the best combination of parameters such that the model performs good. So we can apply that, and we have explored that also as in how to do that. But yes, so we the intent of today's problem was to learn how the LSTM model works. So we saw that how it works, and that seems to solve the today's intent, which is also good, and also learn how LSTM is different from RNN model. So yes, what we can do what commit the code day 17, and maybe I will leave it up to you guys to improve the performance. You can go through the day, which day, yes, day 7 video, and check out how we have applied hyper tuning on our models to find out the best combination of parameters, and that you can apply and maybe improve the performance, and let me know if that method works. If not, then I can maybe try more methods to improve the performance. So I'll go and commit the code. So uh, explore, build and train LSTM model, and this is day 17, and day 17, and we push it and we check this out if the code is there. Yeah, the code is there. So yes, the intent of today's problem is solved. We also learn how the embedding works. So that is also a good thing to learn. Overall, the day is going really good. Tomorrow we are going to come back and add mechanism to LSTM model, today's model for machine translation. So that we are going to split into day 18 and 19. We will tomorrow explore only the theory part. On to day 19, we are going to continue with the coding part. So do come back. We are going to have a great day 18 and 19, and days after that also. But yeah, thank you very much.